welcome back. We are continuing module 2. In this module, we have emphasized that electronics are way too slow to measure both pulse electromagnetic oscillation as well as intensity profile. If we try to measure a pulse with the help of electronics, then what might happen? A time sensitive detector emits electrons in response to photon. Let us say photodiode we can consider, and a photodiode, whenever I shine light on it, it will give me an electrical response, and that electrical response can be monitored with the help of an oscilloscope. Time sensitive detectors including photodiodes and photomultiplier tubes. They are way too slow, that we have already pointed out. They have very slow rise and fall times, and that gives you the response time, which is nanosecond. So, the whole procedure, how long does it take to capture the light from here and plot it in oscilloscope, this whole time scale is going to be 1 nanosecond. Let us assume that it is 1 nanosecond. Therefore, if I have a pulse of 100 microsecond duration, then with the help of electronics I will be able to see 100 microsecond pulse. I will be able to plot it, because for an 100 microsecond pulse electronics is faster and I can plot it. For 100 nanosecond pulse I can plot it and I can see 100 nanosecond. But if I shine femtosecond pulses to the photodiode, let us say 100 femtosecond pulses going to the photodiode, then what will happen? Photodiode and oscilloscope both will show me a pulse of 1 nanosecond, that is all. And this is a big surprise. Okay? Electronics cannot measure the variation of this 100 femtosecond variation of the profile. It will just give me a slow response of its own, which is nanosecond response. So, any femtosecond pulse we try to monitor with the help of electronics, that will become broad response, electronic response in the oscilloscope. We cannot just measure the intensity profile with the help of photodiode coupled oscilloscope. But if it is nanosecond pulse, I can measure, because the response time is equivalent to the nanosecond. Slow detectors, I have already pointed out, always we will measure time integrated intensity, time integrated intensity. So, V signal, if it is a slow detector, then what I will get is a time integrated over minus infinity to plus infinity IT dt. This is what I will measure, and this is nothing but energy content of each pulse. What I measure is basically can be connected to the energy per pulse. Thus, detector output voltage is proportional to the pulse energy only. The slow response time of available time sensitive detectors does not permit us to make time domain intensity profile measurement of ultra fast pulse. We cannot measure just femtosecond pulse or picosecond pulses with the help of the electronics. We have to use the pulse intensity profile to measure its own intensity profile, and this kind of measurement is called intensity autocorrelation measurement. So, I have, let us say, 100 femtosecond pulse. What I have to do, I have to use this profile to measure another 100 femtosecond pulse. I am correlating this pulse with this pulse, that is why it is called correlation measurement. And this is the only way one can measure an ultra fast pulse with the help of slow detector. Then we do not have an issue. We have a slow detector, but we are correlating two pulses, short pulses, and we get this autocorrelation measurement. One of the simplest technique by doing autocorrelation measurement is that we can use 50-50 beam splitter. This we will study very soon in the pulse measurement content. In the context of pulse measurement, I can have 50-50 beam splitter. 50-50 beam splitter will split the beam by 50% of its parent intensity, and then I can reflect back, and then I get these two pulses. Now, depending on the path length difference between these two arms, this is more like a Michelson interferometer, and depending on the path length between here to here and here to here, this path length difference will decide what is the delay between two pulses. And this delay, as a function of delay, if I use a BBO crystal and produce 400 nanometer from 800 nanometer, these are parents are 800 nanometer, let's say, then I can check with a power meter how much energy I get. Then I can plot as a function of tau. As a function of tau, I can plot this energy of 400 nanometer beam, and I can get a points at different delay. And this is a profile which we call autocorrelation profile that can be directly connected to the intensity profile. That can be done. So, this is a way to measure the pulse. Direct measurement with the help of electronics is not possible. We have seen that a Gaussian envelope can be used to represent an optical pulse field envelope, that we have seen. We will draw one more time. This is an important concept. We should remember that if I plot a pulse, I'll plot it like this way. This dot line is the field envelope, then this green line is the carrier wave oscillation, and this blue line is representing the intensity profile of the pulse, which is similar to the field envelope profile, but they are slightly different. And whenever we say pulse duration, we have to remember it is the full width half max of the intensity profile. This delta t is the pulse duration connected to the full width half max of the intensity profile. So, now this is representing an isolated propagating pulse, and this Gaussian function representing the envelope function. Intensity can be given by this, because I is nothing but E is star multiplied by its complex conjugate. We have seen already in this module that this is the expression which is valid for the intensity profile, and then we can always get Fourier transform of this time domain pulse to get the frequency domain. So, which means that I can get Fourier transform of this time domain pulse and I get the frequency domain. And once we get the frequency domain field, then I can again take the power spectrum like this way, and power spectrum looks like this. So, if we look at these two pulses, what does it mean? This intensity profile, if we look at it, intensity profile is centered at t equals 0. This is t equals 0. Profile looks like e to the power minus 2at square. On the other hand, corresponding spectrum after Fourier transform, corresponding spectrum which we measure is S omega, not E omega. S omega when we measure, that is also Gaussian. A Gaussian Fourier transform is another Gaussian, but it is centered at now omega naught. We have to remember that, and that is why the expression for this Gaussian is going to be e to the power minus omega naught whole square by 2a. So, that is the expression we get for the spectrum. Their positions are different. One of them, the spectrum is centered at omega naught, and temporal intensity profile is centered at t equals 0. Now, these are the things which we are already familiar with in this module, and we have seen that this delta t and this delta omega, they are related. Delta t, delta omega, they are related. This is called time bandwidth product. We will come back to this time bandwidth product one more time to understand more details of it. Often in the previous slide I have shown that the spectrum was represented in the omega domain, which is centered at omega naught. But often when we talk about spectrum, we represent spectrum in the lambda domain, which is the wavelength domain. And it is instructive to understand how to convert this omega domain spectrum to the lambda domain spectrum. And that can be done very easily. Omega, which is angular frequency, which can be represented by 2 pi nu. Nu is optical frequency, which is nothing but 2 pi c by lambda. Now, if we take the derivative d omega, then we get minus 2 pi c by lambda square d lambda. And this is an important realization. Whenever we are converting frequency domain to the lambda domain, we have to think about along this line only. Now, we know that area under the curve would be the same. Area under the curve representing the probability, representing how many such system are contributing. So, that will be constant always. Area under the curve does not matter which domain we represent, they should be the same. So, with this idea, we can make this area under the curve to be the same and integrated area under the curve for both domains, and then we can represent it like this way. And once we represent it, then we get S lambda, which is spectrum represented in lambda domain, can be converted to the spectrum represented in the omega domain, or vice versa. Both can be converted with the help of this equation. So, this is a simple mathematical trick we need to employ to convert the omega domain spectrum to the very frequently used lambda domain spectrum. While dealing with pulse intensity profile and the spectrum, we have shown that the intensity profile, this is delta t full width half max, that is called pulse duration, and in the omega, this is omega naught, this is t equals 0. So this is delta t and this is delta omega, and this delta omega is related to the bandwidth, and delta t is related to the pulse duration, which is intensity full width half max, or the temporal duration of the pulse. So, this is pulse duration, and this product has a particular meaning for a particular pulse, delta t, delta nu. Instead of omega, we can write down delta nu. We can convert omega to delta nu very easily, 2 pi nu. So, delta omega is going to be always 2 pi delta nu. That is all. We can convert that very easily. So, these two delta t, pulse duration, and delta nu bandwidth, they are related, and they are related by this time bandwidth product. This concept is very important concept for the ultrafast optics and spectroscopy. The product of the temporal and the spectral width is called time bandwidth product. We have seen that for a transform limited Gaussian pulse, the time bandwidth product is going to be 0.441. This is the time bandwidth product for a Gaussian pulse. This relationship, which is similar to time energy uncertainty principle in quantum mechanics. Time energy uncertainty principle in quantum mechanics looks like delta E delta t is going to be h cut by 2. So, it is quite similar to this uncertainty principle, which suggests that the shorter pulse requires a broader spectrum. Time bandwidth product is minimum for a transform limited pulse. So, when I have this equal sign, which means that the pulse is transform limited, or pulse is transform limited. What does it mean? It means that for a given spectrum, this is the shortest duration pulse I can have. I have often seen student will confuse in this time bandwidth product concept when they are thinking about time bandwidth product. We have to remember that delta nu is the cause. I need the bandwidth to produce a pulse, and this is called effect. So, the right terminology is always to say that in order to get a short pulse, I need large bandwidth. Sometimes by mistake we say that if I can reduce the pulse duration, the bandwidth will change. I cannot change the bandwidth. Bandwidth is something which is a characteristic of the source. So, for a particular source, if I have a source, for a particular source, delta nu is constant. With this delta nu, I can have infinite possibilities of pulses. I can have a pulse like this, I can have a pulse like this, I can have a pulse like this, many other possibilities. But I will have one possibility, one pulse having the shortest duration, and in that case only delta t delta nu is going to be 0.441. Otherwise, delta t delta nu is going to be greater than 0.441. So, for a given source, for a given bandwidth, when I have this delta t delta nu equals 0.441, it means that I have been able to obtain one shortest pulse for a given source. If I do not get the shortest pulse, then the pulse duration always be longer, and that's the consequence of this time bandwidth product. But question is, this derivation we have seen in this module already, and the question may come whether we always need to use a Gaussian pulse to represent the intensity profile, because this equation is valid only for Gaussian pulse. This equation is not valid for any other pulse. And one more point I'd like to make here is that although this equation is similar to the time energy uncertainty principle, Heisenberg time energy uncertainty principle in quantum mechanics, but we cannot get this number from this equation. We have to use the derivation which we have shown in this module for the Gaussian pulse. And question is it always necessary to use a Gaussian pulse to represent the experimental ultrafast pulse? So far we have seen that the Gaussian pulse envelope is, when we consider Gaussian pulse envelope, the time bandwidth product becomes delta nu delta t equals 0.441 equals greater than equals 0.441. That's the, if it is equal, then we get the shortest duration pulse for a given spectrum. Now, Gaussian envelopes are most commonly used in ultrafast optics because subsequent analytical math becomes very simple and they very closely represent an experimental ultrafast pulse. However, it is not necessary always that we have to consider a Gaussian field envelope. It is not always necessary. One can assume many other pulse envelopes which may closely represent an experimental pulse. Selection of the appropriate field envelope depends on the experimental observation. For an example, one can say that a rectangular pulse can also be another way to represent an ultrafast pulse. Rectangular pulse like this. I have nothing, 0, then suddenly I have this V naught value, then again coming down 0. So, this is your 0 and this is your V naught. This is rectangular pulse. A rectangular pulse is commonly used in electronics and in signal transmission lines. We can also consider this kind of rectangular pulse to represent an ultra-fast pulse theoretically. We can take a look at the time bandwidth product for this rectangular pulse. Procedure is known to us now. A rectangular pulse is depicted here, and Vt is represented by Vt. That's the temporal profile of the pulse. And we know that when we get this V naught, the maximum amplitude at this time only, these two times, t minus t by 2 and t by 2. It is centered at t equals 0. And this pulse can be represented by these two equations. Why these two equations? In two different limits, their values would be different. If Vt, if t, this modulus of t, the magnitude of t is greater than t by 2, then I get 0 value. All this voltage will be 0. But if this magnitude of t is less than equal t by 2, then I get this V naught, the constant value. And that's the way we can represent the rectangular pulse. From theory of interference of plane waves, it is already known that a pulse is originated due to superposition of many pure waves, frequency components. So that is true for even rectangular pulse, which is shown here. So in order to produce this kind of rectangular pulse in femtosecond domain, let's say, it's an hypothetical idea we are discussing here. Let's say we are producing this kind of rectangular pulse in femtosecond domain. Then we have to consider that this pulse was produced with the help of many frequency components, because only optical way one can produce pulse is the interference. And we can immediately convert this time domain pulse to the frequency domain by Fourier transform, which would look like minus infinity to plus infinity time domain representation multiplied by e to the power minus I omega t dt. So I can get this frequency domain representation. As a representative example, we have considered here an ideal rectangular pulse which is centered at t equals 0. So this is t equals 0, which is centered, and Fourier transform of this function will get V omega equals minus infinity to the limit. We are considering limit to be minus t by 2 to the limit of t by to minus t by 2. From this minus infinity to this limit, we have this Vt. We are separating the regions because there are two regions we have for this rectangular pulse, omega t dt, plus there is a region which is within this limit, which is nothing but minus t by 2 to plus t by 2 Vt, then e to the power minus I omega t dt, plus the other limit where limit plus t by 2 to plus infinity limit, that is Vt e to the power minus I omega t dt. Now we know that this limit, in this limit Vt becomes 0, in this limit Vt becomes 0. So only term which will contribute to the Fourier transform of this pulse is going to be minus t by 2 to plus t by 2 Vt e to the power minus I omega t dt. This term will contribute. So if we integrate it, then what I get is that V naught, this value is always constant within this limit, V naught multiplied by minus t by 2 plus t by 2, then e to the power minus I omega t dt. This is what we get. And further we can write down this integration, we can simplify this. So V omega, what we get is V naught divided by minus I omega e to the power minus I omega t, which is plus, sorry, this is minus t by 2, this is plus t by 2, and within this limit. So if I insert it now, I'll get V naught divided by I omega into e to the power I omega t by 2 minus e to the power minus I omega t by 2. And this expression, we know this expression, this is like e to the power I theta minus e to the power minus I theta, which is nothing but 2I sin theta. We can write down this V naught divided by I omega 2I sin omega t by 2, which can be rewritten as V naught t sin omega t by 2 divided by omega t by 2, which is nothing but a cardinal sine function V naught t cardinal sine function omega t by 2. This is nothing but sin x by x, which is representing the cardinal sine function. So, the frequency domain function is going to be represented by this cardinal sine function. And if we look at the cardinal sine function, the power spectrum is going to be then the power spectrum can be represented by this PW, which is nothing but VW square modulus and of B omega, which is nothing but V naught t whole square cardinal sine function square omega t by 2. The power spectrum is plotted here, and this is the plot we have, and it is evident that Vt, the rectangular pulse, contains many frequency components. All these frequency components extended up to plus infinity we have, okay, theoretically. So, theoretically from 0 to plus infinity, all these frequency components we have. The amplitude of a cardinal sine square function decreases by a factor of half when this omega t by 2 becomes 1.39. This is very well known number. We will use this number in nonlinear optics as well. Any cardinal sine function, when you write down this sine x by x, which is nothing but cardinal sine function, this cardinal sine function will drop to its maximum intensity when x is 1.39. So, we can use this only positive component of the frequency. See, negative frequency is nothing but mathematical artifact. It is just as given to me because we have taken the both complex conjugate and the complex number. So, we have to avoid considering this negative frequency component. Negative frequency does not mean anything. We have to consider only positive frequency component, and we would like to find out what is the full width half max for this. And for that, we are saying that it is delta omega t by 2, that is nothing but 1.39, coming from this characteristics of cardinal sine function, and from that we get the time bandwidth product of a rectangular pulse, which is nothing but 4.443, which is quite similar to quite similar to the ultra fast pulse for a Gaussian pulse. We'll stop here and we'll continue this module in our next lecture.